So our next speaker is Priscilla Frisch from the University of Chicago, and she will be talking on following the interstellar magnetic field from the heliosphere into deep space.
So I'm going to talk about a new perspective on the interstellar magnetic field that some of you may have heard of before. And, but before I say that, I have to say I was wondering why the organizers decided to have this meeting right before Memorial Day. And I went back and noticed that one of Carl's first papers was on the polarization of moonlight. And it turns out that last weekend there was a blue moon. So that must be why it's being held this week. So anyway, so what you see up, the background image is an image, it's one of the first visualizations of the three-dimensional heliosphere. You see the bow shock, you know, the big, huge purple envelope. And I'll go to this image, and then you see a little tiny olive, and that's where the solar wind goes from being supersonic to subsonic. That's called the termination shock, and the Voyager spacecraft have both passed that. And that the first piece of information that we have, I think, the really good information about the asymmetry of the heliosphere caused by the interstellar magnetic field is the fact that Voyager 1 and Voyager 2 cross the termination shock at different distances of 95 astronomical units in the north and 85 astronomical units in the south. So this is a picture you're much more familiar with. The nose of the heliosphere, which is defined by the inflow, the heliocentric inflow of interstellar neutral helium into the heliosphere, is very close to the center of the galaxy. If you convert the heliocentric velocity to the local standard of rest, what you discover is it's coming from a direction that's very close to the center of the Loop 1 supernova remnant. I won't talk much about it today, but it turns out the interstellar magnetic field direction that we get from all of diagnostics is perpendicular, almost pretty close to being perpendicular to the velocity of the local interstellar gas within 10 to 15 parsecs to the local standard of rest. That indicates to me personally, and this is supported by models, that the sun is actually sitting in the shell of a superbubble remnant. So that's the other connection to the work Carol has done. I was his first graduate student, by the way. So anyway, so here's an early paper where he talks about the uniform versus the random component of the interstellar magnetic field. What was random on the scale of the galaxy, in fact, is uniform on the scale of the very local interstellar medium. And I'm going to talk about polarization and there are two new diagnostics, and that's the direction of the interstellar magnetic field from the heliosphere and from the IBEX Ribbon. And then we've done a polarization survey of the polarizations of nearby stars, trying to determine the interstellar magnetic field in the interstellar clouds near the sun. Starlight is polarized by aligned dust grains, and the assumptions made in all of our analyses of the polarization data is that the polarization position angle is parallel to the direction of the magnetic field. I know that there are different studies that show that radiation has an effect, but I don't understand the impact of that. So a brief introduction about the heliosphere. You see that the IBEX, the satellite Interstellar Boundary Explorer mission, which has been mapping the interaction between the interstellar medium and the heliosphere, which is the solar wind bubble, is measuring energetic neutral atoms. We call them ENAs. And an energetic neutral atom is formed when an ion that is gyrating around the magnetic field charge exchanges with an interstellar neutral. And the ion steals the electron from the neutral and creates a very high energy neutral atom and leaves behind a special population of plasma. The energetic neutral atoms measured by IBEX go up to from 0.1 up to 6 keV. That corresponds roughly to 50 or 100 kilometers per second up to 1,200 kilometers per second. And so the magnetic field direction that we get from the IBEX ribbon, oh, and by the way, this is an MHD simulation showing the Voyager 1 spacecraft, very much above the nose of the heliosphere, Voyager 2 spacecraft, and the interstellar magnetic field draping over the heliosphere. And the reason this is of interest is we will see in the next slide that when IBEX was first launched, it discovered a great, huge ribbon of energetic neutrals in the sky, and comparison between the location of the center of the ribbon and the interstellar magnetic field direction that we were getting out of MHD heliosphere models showed that the center of the IBEX ribbon is tracing the direction of the interstellar magnetic field that's shaping the heliosphere. This is an energy-dependent direction, so the best values actually come out of simulations. And the direction that you get from the latest simulation of the direction of the interstellar magnetic field in galactic coordinates is towards 26 degrees longitude and 50 degrees latitude. The magnetic field strength is 2.93 microgauss, which is exactly the magnetic field strength that you would expect for the kind of low density, partially ionized field that the sun is sitting in right now. The density is 0.25 atoms per cubic centimeter, and it's 25 to 50% ionized, depending on whether you're talking about hydrogen and helium. And this is I think that's an excellent magnetic field strength that it agrees with other diagnostics. You'll notice that the direction of the magnetic field is towards the North Polar Spur. Let's see. Okay. Well, the direction is towards the North Polar Spur. The only direction in the sky that I know of where the interstellar polarization strengths increase steadily with distance is actually toward the North Polar Spur, which is also consistent with the view that that there's a dust bridge between the North Polar Spur, the more distant regions, and the sun, and that dust bridge is part of a supernova bubble. Okay, so we've undertaken a survey of linearly polarized starlight. The collaborators, Bilpu, Berdyugin, and Mario and their students in the southern hemisphere have acquired a large number of new data for this survey of stars within 40 parsecs. We chose 40 parsecs because most of the interstellar gas that we see in the UV, ultraviolet, and optical absorption lines that's really close to the sun is within 10 parsecs. But to get enough buildup of magnetic field strength, we went out a little bit further. So I want to give credit to the Brazilian government, the Japanese government, the US government, and whoever's running Canary Islands for maintaining the telescopes where these measurements are being made. So here is a map of sort of the latest set of data that we now have. What you see are the stars with positive polarizations, which I'm defining as having a signal to noise or a polarization versus over a mean error of 2.0, which is a very generous definition. They're all plotted with the little fans. These little fans give the uncertainties on the polarizations, and all of the dots are null points. Now, we have a lot of data from Carl's survey, from his compilation of all the 20th century data, and the mean errors on a lot of those data points are much larger than they are for the beautiful new data that's being collected. And so just because you don't see a polarization vector on a point doesn't mean it's not polarized. It just means it was not detected in that particular measurement. What you see right here is the IBEX ribbon, the brightest part of the IBEX ribbon, which I have put on my figure because that was the original motivation. And we started out by sampling stars that really trace the IBEX ribbon. Okay, so what is most important here are these little directions right here. This is a summary slide, and I'm going to review how we actually pull a magnetic field direction out of the polarization data in a minute. But this little X shows you the direction of the polarization that we get out of the direction of the interstellar magnetic field within, say, 10 parsecs that we're getting out of the polarization data. The B shows you the direction of the IBEX magnetic field, which actually is energy dependent. And the X's right here show the direction of the magnetic field that you get from pulsars 100 to 300 parsecs away. This is a paper by somebody named Salvati in 2010. And he basically did a best fit to a very small number of pulsar dispersion and rotation measures. And he found a pole for the magnetic field that's extremely close to the pole we're getting from the polarization data and from the IBEX ribbon. And this, that's like 10 degrees. And so we're talking about a magnetic field that's coherent over 100 parsecs that has a similar direction. And so now I'll go into a few of the details. In order, because the polarizations are so weak, we had to analyze the best fitting magnetic field direction statistically using a statistical weighting function. And basically what you do is, what was done is we rotated the interstellar magnetic field direction to every possible direction in the sky. We started initially only with the galactic center hemisphere because that's where the IBEX ribbon was strongest. And if you do that, and if you properly weight the uncertainties on the polarizations, it's not Gaussian because the polarizations are based on the Stokes parameters, which are positive and negative, but the polarization, of course, is always positive. It's the harmonic mean of the two of the parameters. And so you find the minimum of this function. We call it the merit function. And the assumption here throughout is that the polarization position angle is always parallel to the magnetic field direction. If that is invalid, then we have to rethink what these results mean. And here's a plot. This is a plot of the merit function over the whole sky, and there's a very distinct minimum with uncertainties, I'd say, plus or minus 5, 10 degrees located in this direction. And this is actually an old result. We published it last year, and we're going to get a better result. We have a lot of new data since then, so we expect to have a better result. Now, the probability, what's important to know about the direction that we have quoted is that this is the probability distribution for all of the polarizations to actually trace this direction. Here you see 3355, which is one of the earlier values, but the essence is the same. The blue points show polarizations with signal to noise of 2.0 or larger. And you see there are a huge number of stars that have polarization position angles that are very consistent with the IBEX magnetic field direction. But there are also a lot of stars that don't. And they have statistically significant polarization. Some of them might be intrinsically polarized stars, but clearly there are other components of the magnetic field. Now, what I forgot to mention is that in the minimum, in the application of the merit function that I just showed you, we've done it both with the entire data set and also after taking into account this magnetic structure. And it turned out we got a much better match to the IBEX magnetic field direction if we took out a very special polarization filament that is well defined. And that particular polarization filament actually looks like it's a filament of dust around the heliosphere. Okay, so I'm jumping ahead now to the polarization filament. We originally picked out the stars for the polarization filament for a slightly spurious reason. I thought the magnetic field direction was going to rotate with distance because we were part of loop 1, but it turned out what looked like it was a rotation with distance was in fact this filament that was really close to the sun. You see it in stars within 5 parsecs, several stars within 5 or 6 parsecs. And here are the polarizations of the polarization filament. This is the IBEX ribbon again, and various magnetic field directions. And there's a lot of stuff that's related to the heliosphere that you can ignore. We applied the merit function to the filament stars, and you get an air box just like this. The nose of the heliosphere is right here, and so the air box included the nose of the heliosphere. The other aspect of the polarization filament, which is extremely interesting, is it is perpendicular to what we call BV, where here B means magnetic field and V means velocity. It's perpendicular to the fundamental asymmetry plane of the heliosphere, which is this BV plane. This is the elongation to the filament, so it's almost exactly perpendicular. And you can only have those two properties where the magnetic field direction points towards the inflowing gas velocity, and the symmetry of the filament is perpendicular to the BV plane. You only have that of the filament of dust that's around the sun. Now this dropped out of the data. Believe me, I never expected, in my wildest imagination, never expected that we would see anything like that. The BV plane is easy to understand. It's easy to understand why that is a fundamental symmetry plane, because B cross V gives you the Lorentz force, and the plasma in the heliosphere is entirely a plasma system, so all of the outer heliosphere aspects of the heliosphere are governed by the Lorentz force. So it makes total sense, and I'm not showing it to you, but there's a lot of beautiful models showing the configuration of interstellar magnetic fields draping over the heliosphere, and there is one of the configurations that goes north-south, I mean, that looks like it exactly traces this elongation. We haven't actually done that comparison yet, but that's in the future. So I have another, I'm going to skip over this slide, and I'm going to skip over most of this slide. I did want to point out that we have a 2012 paper with John Slavin as the lead author that simulated the trajectories of interstellar dust grains through the heliosphere, and he actually predicted that there is a set of interstellar dust grains. They have very small gyroradii, and they're excluded from the heliosphere. They cannot enter into the heliosphere, and they form plumes. The models we were working with had single polarities for the solar wind. And so I'm going to turn to the TeV cosmic rays. There have been a lot of studies of the flux of cosmic rays with energies 10 to 20 TeV into the heliosphere. There was an early study by Milagro and several other, let's see, this is the observed one that had a very bright hot spot right here, and the latest HAWK is not as in the infrared HAWK, but high altitude Cherenkov counter or something. Anyway, in Mexico, where they found that this is a point, they have beautiful spatial resolution, so region A is a very well-pronounced maximum in the flux of TeV cosmic rays into the heliosphere was measured by HAWK. And this direction is almost exactly opposite the direction of the pole for the interstellar magnetic field that you find from IBEX and the other data. So that's not surprising, because the gyro radius of these TeV cosmic rays are less than a few thousand astronomical units. Now, Nathan Schwadron actually attacked this whole problem before we had the HAWK data, and he modeled the propagation of TeV cosmic rays through the heliosphere, and he showed that you see exactly the same kind of dipole asymmetry that you see if you combine, ice cube in the south and all of the northern hemisphere cosmic rays. Cosmic ray detectors. So I think we can say very, very reliably that the heliosphere magnetic field is determining the spatial configuration of TeV cosmic rays in this energy range.
Priscilla.
Okay. So I already talked about the pulsars. There's the paper, and I will show one more picture.
Let's have a question.
Okay. I'll leave it at that.
Let's have a question. Anybody? Question? Okay. Oh.